one last thing. Let me get the headphones. Okay, mute. All right, guys, and we are live. Just to let you know that this is being recorded. However, nobody can see your faces and nobody can see the chat. So if you have any questions, the best place is to drop them in the chat, but you can also ask them in a video format. I'm going to pause roughly every 7 to 10 minutes. So let's begin. Fractals. So what is a fractal? A fractal is a curve or geometrical figure, each part of which has the same statistical character as the whole. Well, that is the definition from the Oxford Dictionary. But as you can see, like in all of these pictures, these are very, very simple geometric examples of fractals. You have this sort of trident, and then all of a sudden, each dash splits into a trident, and then each dash splits into a trident, and you arrive at this fractal shape. So it's the same pattern, repeating again and again on a smaller scale. So fractals exist everywhere actually in nature. Now, mathematically, they were first defined back in 1975 by a guy called Benoit Mandelbrot. So Mandelbrot defined this geometric term that fractal was a shape with a confined surface area or volume. They could be three-dimensional, but an unlimited complexity on its outside edges. And to be honest, nobody thought that fractals were super interesting until the late 70s. So they started to draw them by computers. This is the first ever fractal drawn by computers in 1978. Now, one thing that was observed from the very, very beginning, ever since this was mathematically defined, was like, hey, well, we have a lot of fractals in nature. The structures of leaves, trees, rivers, tornadoes, clouds, so many different living things, be they plant or animal, or even natural phenomena, tend to have fractal patterns. Now, what really turned into a game changer in terms of fractals was in 1980, they started to put them into computer simulations together with randomness. Now, I wanted to pause that. So I'll tell you a little bit about this animation because it changed the world completely. So this is 1980, and a guy called Lauren Carpenter is working for Boeing. And Lauren is trying to create a background for an airplane. Now, he read Mandelbrot's book and he figured maybe he could do something in a three-dimensional space using fractals. So he constructs this landscape. It's made of 50 triangles. And using a fractal method, he will split each triangle into 4. So if this is a triangle, sorry, I'm horrible with drawing with the mouse. He is going to split it like this. Boom, boom, boom. And then give each dot, each corner here, a slightly randomized elevation. So a landscape of 50 triangles becomes something spectacular when the fractal method is applied. So this, by the way, in the 1980s computers took days to render, but in today's computers, this would be virtually instant. And it went from 50 triangles to 5 million, and a very, very realistic three-dimensional fractal landscape. So this 1980s animation has changed the way that we construct three-dimensional graphics. So ever since this happened, I'll just clear the annotations. Lauren Carpenter, who created this, left Boeing and went on to co-found Pixar. So these types of three-dimensional structures are everywhere in Pixar movies, and they made their way into video games. So this combination of fractals being simulated in a three-dimensional computer environment together with some randomness can allow computers to create these wildly realistic landscapes. So this is this image is from the Brave Pixar movie. This is from Assassin's Creed. And this one right here is probably the most interesting by far. There is a game called No Man's Sky. And No Man's Sky uses fractal geometry and randomness to create a universe with millions of totally unique planets with unique wildlife, unique plant life. So this game itself, although it hasn't been wildly popular in terms of sales, has led a lot of people to speculate that, hey, maybe the universe is a simulation, because look what we could do with some computer power and fractal geometry. We could create whole virtual worlds, which are looking ever more realistic. So just think back to what a fractal is. It is a pattern repeating itself on a smaller and smaller scale. And what's interesting and what this workshop is about is going to be trying to replicate these using very, very simple computer code. So we're going to use Python and a library called Turtle. So Turtle itself has just a very small number of very simple commands: forward, backward, right, left, go to, pen down, pen up. And together with Python, we're going to use it with loops, lists, and the random library. And we're going to use that to create various shapes. We'll begin with just, two simple squares, lifting the pen up and down. Then we are going to use the loop variable and fill in the shape with a particular color. After that, we'll convert that shape to a function, a polygon function, and create our first fractal. Now, if you look a little bit closely, this is a pentagon, and it draws twisted to the left, a slightly smaller pentagon, twisted to the left, a slightly smaller pentagon, twisted to the left, a slightly smaller pentagon, and eventually you end up with this beautiful fractal pattern. And we can fill those with colors and make them into various structures that resemble things like horns and cones, for example. We'll also create this very, very famous fractal that's called the Sierpinski Triangle. The Sierpinski Triangle is basically a trident that keeps dividing, but we'll also play around with using stamps to make it look a little bit more filled in. After that, we will get into drawing a simple fractal tree. Now, a simple geometric tree is essentially this V shape right here. Let me annotate. If you can draw the V shape that I'm sketching over right now, and if you let that V shape repeat itself, you're going to draw a tree. And that tree can get really realistic if you were to randomize the angle in between these and randomize the branch length. So I'll clear the drawings, and you're going to see that on the next slide, we can create an essential factory of unique trees in merely 26 lines of code. So this should be the highlight of the workshop. This is going to be what we wrap up with. Now, before we start coding, I'll play a little video that is going to show you how you can try to split your screen. So the goal is going to be that I will show you my code on half a screen. I'll actually have my code stacked like this, and your code, you could code along with me on the other half. If you can't catch up, it's really, really easy. You just have to enter this bit.ly link to the Python program that's going to be in the browser. So I'm going to make sure that I am sharing computer sound. Just drop me a message if you can't hear it for whatever reason. This is going to show you how to split screen in Zoom. And then we are going to, we're going to get started with coding some fractals. Hello, everyone. When I share my screen, it is going to look like this. I will share a code that's about half a screen size, and you may or may not be full screen. So you should exit the full screen and try to resize Zoom to be half of a page. You can even zoom into the code like this. So shrink your face as much as possible. Now you see my code really well. So after you've done that, you're going to open up your own Chrome tab. and put it next to mine and copy this link. bit.ly bot guest. Now, we're not going to start with bot guest, but you're going to copy whatever link I have on the screen. And guess what? You'll be able to modify this code. This is going to be your own copy of the code. You'll be able to change your settings here, and it's going to be your own program. I hope that makes sense. Okay, so let me exit out of the presentation and open up my Chrome. So that's going to go there. I'm going to close that. So this is the link you should try to put into your browser. Oh, I need to share screen. Sorry, guys. Share screen. Okay. So this right here, this link, you will enter into your browser and you will be able to get the same code that I have. So bit.ly turtle intro, you will put it in there. In terms of how this works, you'll be able to bookmark this link. And with the bookmark, you'll be able to basically get back to your code. These temporary, your user here, after you bookmark it and change anything, is going to turn into anonymous. And you will be able to basically access your code whenever you need it. So in this very, very first one, I have already put in some code. I'll rewrite it. Close that. So this just draws a square using turtle.forward, turtle.left. It also uses a Python loop. So let me show you what in essence we're doing. So if we said turtle.forward 100, that will draw a straight line of 100 pixels. If we said turtle.left 90, that would turn the head of the turtle, like the actual turtle, by 90 degrees. And if you were to copy and paste this 4 times, you would draw a square. So already you see a bit of an application for writing a proper loop. And the way we write a loop in Python is we say for I in range 0, some number. Now, what this is going to do is everything that's indented after it will repeat 4 times. So what do I mean by indented after it? I can highlight it, press tab, run it, and we've got that effect. So the very first thing I want to do now that we've drawn a little square is play around with the goto function, going to a specific location and lifting the pen up. So let's just say we want to lift the pen up, turtle.pen up, and turtle.goto. Now, turtle exists on a Cartesian plane. This is 0, 0. So you can go to a place in this sort of geometric grid, like say -100, 100. And then you can try to draw another square. But that one isn't actually doing anything. Anybody in the chat want to guess why this code here isn't leaving a trace? Let's clear the annotations, clear all drawings. Well, it isn't doing anything because the pen is up, and you can put the pen down. Turtle.pen down. One thing that's tricky with turtle being displayed inside REPL is that everything that happens after this dot turns purple. So you can actually write some function name that doesn't exist that's also going to be purple. So you really have to be careful. Color coding won't help you. You have to get the spelling absolutely right. And when we get into the colors, you have to spell color the American way, C-O-L-O-R. So before we move on to our first fractal, I just want to also demonstrate coloring and how you use this I variable. So I'm going to get rid of this code. And I'm going to use color now. So we'll say turtle dot color, C-O-L-O-R. Let's say green. Okay, so we have green color. Now, we can fill our shape by typing in turtle begin fill before the shape begins to be drawn and turtle end fill after the shape is finished drawing. So begin underscore fill. And a bit of recycling here. Now, I prefer to just maybe leave a space. These spaces in Python make no difference whatsoever, but this would be turtle end underscore fill. So yeah, that's a green shape that's filled in. You can also specify different pen colors and fill colors. So you can have pen color that's green and fill color that is purple, whatever. So if you're following along, this would be a good thing to try here, would be to try out different colors. Turtle knows over 500 colors. Yeah, so most of the ones that you'd imagine, cyan, teal, magenta, all of those actually exist. Although sometimes you might run into one that doesn't. But before we move on to actually drawing our first fractal, I got one more thing to show you. You notice how this eye is in there. You might be wondering what the eye does. Now I'm going to write an extra line at the end of this shape just to demonstrate how loops work. So for I in range 0, 10, print I. The reason why you use I and not some other letter or name is because I stands for an integer. So a loop has this built-in integer counter that we can use in our shapes. It starts off at 0 and it ends at a number that's 1 less than that limit. So look at how we can use I. Instead of going forward 100, we can go forward I. And instead of making that 4, we could make that 100. Now, this is actually going to draw a neat little, now you can't see the fill because of the line thickness, but it's drawing a spiral, a square spiral. And if we sped up our code, turtle.speed 100, that would get drawn extremely quickly. So let's now take a really quick look at how we can actually have some spaces that could be filled in. All you would need to do is multiply I by some number, maybe 3 or 2. Have a look at this. And here we go. That is a spiral, a square spiral that is filled in. The spiral could change just by changing this angle here. So if it was 45, it wouldn't be a square. It would be some kind of an octagonal spiral. If it was 120, it would be a triangular spiral, and so on. So let's now take a look at how we can use the simple loop structure into how we could restructure that into a function that draws polygons. Because once we could draw a polygon as a function, then we can use recursion, which is that same pattern repeating at a different scale, and we have fractals. So this is where we're headed. This is what we're going to draw next, that famous pentagon spiraling in on itself. This is the code that you have to enter. If for some reason it doesn't work, you can always try that second code. But I will prefer to start this from scratch, not total scratch, actually from total scratch. Why not? So this time around, I have imported turtle differently. If you type in from turtle import star, you do not have to write turtle dot pen color, turtle dot fill color. You just have to write pen color, fill color, and so on. So this is a little bit of a shortcut. So to draw that simple square will be for I in range 0, 4, forward 100, left 90. There it is. Given that the speed is 100, it gets drawn instantly. So let's try to systematize that. What do I mean by systematize? Let's say we have side length, and side length is 100. Well, instead of 100, you can just place side length. So forward, side length. And now I can change my side length to be anything. 200, it'll draw a bigger one. Wouldn't it be neat if we could do the same with sides? Now, if sides is 4, I can just place sides there. So that works. What will happen if we change that to 5? Yeah, the turtle is just going to trace over one side an extra time. All right. So that's not quite working. That is because of this angle. That angle multiplied by sides should be 360. So you could basically figure out that that angle is 360 divided by sides. And all of a sudden, pentagon, 6, hexagon, 3, triangle. So just by changing these two things, you can change the shape that you are drawing. Now, let's have a look at how we can restructure this to be a function. So a function has a definition, polygon, that's a function name, and then it has some parameters. And in our case, these are going to be our parameters. Ping. And ping. So that has a colon. And this time you put this for loop inside the function by indenting it. Just one more time, Control Z. You highlight it, you tab it, and it goes inside there. Now, if I run this code, nothing is going to happen. Because a function is a blueprint, and you need to execute on the blueprint, so to speak. So if I say polygon 5, 100, that's going to produce, oh, I did side length then sides. So that was going to produce a 100-sided shape with the side length of 5. I wanted to do it like this: sides, side length. So now the first parameter is the number of sides, and this is the length of sides, and that should be a pentagon. Yay. Nonagon. I don't even know if nonagon is a thing. I've heard somebody say it, but that's a 9-sided polygon. Okay, so at this point, we've drawn a function. Can I just get a message in the chat if you got a question, if you're following? If I get no messages in the next 20 seconds, I'll just assume that everything is A-okay. A fun thing that you could do at this stage is try to go back and use the color to fill in that polygon. All right, so what I'm going to do now, I'll make the side smaller. I will try to make this polygon recursive. I will try to make that polygon, as soon as it's done, draw another polygon. And all you need to do is just copy the function definition right here, backspace a little bit, and put it there. And just say, well, just draw me another one with a slightly smaller side length. And there you go. That's a little recursive shape. Now, this is going to be a bit rough because it's just going to continue forever. Turtle works on negative numbers. So this little recursive polygon is just going to start going on the other side. And this would keep drawing until your browser ran out of memory. So we need to put some kind of a size limit. So if side len is greater than 0, so no negative sides. Oops, Control Z. Run this. So it should be exactly the same, except this time it stops. Ping. And now you could have like turned it left by a couple of degrees, run it. And all of a sudden it has this beautiful fractal shape. And since this time, the one that I've shown initially was about 5 by about 150. So we could draw that, and then I'll show you one other variation of how you can make it look a little bit like a horn as opposed to a shell. And if this one is a shell, because it just turns in on itself, if you are also going forward a certain amount, maybe 3 or 5 or some distance, we can actually draw a different kind of shape. I might have to resize my entire screen to fit it in. Probably would have needed to go forward a bit more, maybe forward 8. Let's try this again. Maybe make that a bit smaller. And this looks like, yeah, I mean, a horn of an animal, I guess. And it's going to narrow down. Now, if you were going to make this shape fill with color, that is possible. You could just put a color here and here, like begin fill and end fill. But what would be better is if we were to say define color, or just fill color yellow. And if we said begin fill, and end fill. So now every circle it draws fills in with yellow. And yeah, I think the shape is just a little bit more interesting. And it's completing. Yeah, I've got a question about the links to these programs. You could just bookmark them one by one, but I'll be sure to send you guys a list of all of the programs that we use. That'll be in the follow-up email along with the link to the recording. And again, my apologies if I'm going reasonably fast. If you're finding this interesting, but you're struggling to follow, again, the recording of this is going to be in your inbox, probably by about 8 p.m. tonight. Okay, so where do we go next? Next, we're going to actually draw the Sierpinski Triangle. We're going to draw that structure. And I might just mess around and make it a little bit more interesting, adding stamps and filling it in a little bit. But let's just start from 0. So again, what you need to do is annotations, take this code right here, put it in your browser. That's going to allow you to basically follow with wherever I am with the code. So if I'm running a little bit too fast for you, every time you put this code in, you're going to catch up to wherever I am. Okay. Sierpinski Triangle, how to do this. What I'm aiming to do is from scratch, try to figure out how to draw that shape. If I can draw that shape, then I can turn that into a function and then make that recursive. So let's begin. So we're going to need a loop for I in range 0, 3. So we're going to have 3 things. And so I'm going to go forward. Let's just say, maybe I'll create a variable from the start. Length equals 100. So I'm going to go forward length. And then I'm going to go back length. And then I'm going to turn 120. Left or right? Let's try left. So there it is. That's that trident. Now, if I didn't have this right 30, by the way, if I did not have that, it would be a little bit tilted. Hence, there is that right 30, and the right 30 tilts it the right way up. So that the goal is, how do we get this to then draw smaller tridents, here and here, and then they're going to draw smaller tridents and so on and so on. How do we get this shape to be recursive? Okay, well, what we want to do is just start by making a function. Clearly, length is going to be a parameter. So def Sierpinski length. It's also going to have something called order. And that order is how many times we're going to go clunk, 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 how many times we're going to shrink in size, how many times we're going to halve the length and draw the trident. So it's going to have length and order. Now, if the order is also known as depth, so you could use the word depth as well. It's another valid name, but we're going to say if order equals to 0, then return. Return basically means finish the function. But if the order isn't 0, we'll do this. And here's the key thing. When we go forward on this end right here, we're going to draw a smaller Sierpinski. So we're going to say Sierpinski, how much smaller? Length divided by 2. And the order is going to reduce by 1. Order minus 1. So that, by the way, we need an else, and that needs to be indented. So, okay, that works. So all I need to do here is say Sierpinski 80, let's see 3 first. Bingo. If you want more detail, make it higher order and it'll draw more little triangles. And if you want to make it look filled out, well, there's a neat trick. We can use stamps, and there is a stamp called a triangle stamp, but let me put this in. If I say stamp, let's say we stamp it. So currently it's using this turtle arrow, but I think the turtle has an option to have a shape triangle. Okay, well, it's all filling out, but I'm sure if we get the size a little bit more refined, we'll have a better looking Sierpinski triangle. So let's try maybe 100, just make it a bit bigger. Nope. What about lower order? Oh, wow. Dun, 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 dun. That's a pretty little Sierpinski triangle. And if you want to pen up at the start, it will just draw these dots. Now, if we were going to program, we can also HT. HT means hide turtle, so we can get rid of that dot in the start. If you were to program this to fill in geometrically, the code would be about, I don't know, 10 times more complicated. So this is almost a little bit of a cheat using this shape triangle, because you got to find the settings that just fit the triangle shape. But it still looks interesting. I'm sure that if I like used 90 or something like that, it wouldn't look like a proper Sierpinski triangle. It would just be a bit overfilled, if that makes sense. It'd be more black than white. I guess 75 would illustrate that a little bit more. Yeah. As you can see, like the triangles are within. But yeah, I think that that looks pretty cool. Again, in your own time, there are some suggestions to editing it. You can hear some ideas. Fill in gaps with colors. There's one. And you could like maybe draw a polygon where draw a square where each side is a Sierpinski. In fact, I'll just show you what I mean by that. I'm not sure if this is going to look good, but so for example, for I in range 0,4, you could do something like this and forward 50. And maybe we'll just make it a lower order to be drawn quicker. There's an error, bad input on line 19. And the comments need to be commented out. But you can combine this with the loops. So I'm drawing shapes that have various triangles. If we were also turning left 90, and if we went forward 100, watch this. These triangles would be turning in on themselves, upside down. And this looks silly, but actually that's not too bad. You can turn these into various patterns by using that same loop structure that we used in this first basic tutorial. And this actually is also valid for doing that with polygons and spirals. Okay, what's next? We're going to draw a very, very basic tree. So this here is an example of a more advanced one. And then with the time that we have left, I will see if I can randomize the branch length and the angle, as well as the thickness of the stem. So the basic tree, what is it made out of? What do you need to draw? What turns into a tree? That. If you could draw that and then make that recursive, so make what I mean by make it recursive, well, next time around, it draws this instead of a branch. Like it's just smaller. And next time around, it'll draw an even smaller one. That's the shape we're going to be drawing. So clear all drawings. So yeah, this time we're going to use random. We're going to use that later. Again, the same rule applies, by the way. Type that in, get my code. Let's begin. So we're going to need to turn left 90 because we got to face up at the start. We want that, yep, pointing up. So what variables does this branch have? It's got length. So branch len, let's make that 100, and it's got angle. Let's start with 30 degrees. So how would this work? You would go forward, branch len, and then you would go left 30, and then you would go forward, but less, some number, maybe 0.7 times the branch length. Boom. So, okay, like it looks like we're halfway there, but we're not really. We would need to go backward. You could change that to backward, or you could just put a negative number there, right? I prefer saying backward because it's just a little bit more intuitive. So if you go backward, then you're going to go, you're going to turn right 60. And then you'll repeat this pattern again, all right? Boom. So you go forward. And now all we got to do is take this turtle head all the way down. And really, we can repeat this left 30 because that will straighten it up. And now we go backward branch length. And there it is. Oh, we didn't go left 30. All right. So this is actually going to be fairly easy to convert to a recursive fractal. We've got pretty much most of it there already. So in fact, def branch, we'll have a branch and it has branch len, it has an angle. Okay, so no errors yet. Now, we are going to shrink the branch length. And we're going to keep angle the same. Now, the trick is, like with every fractal, you got to know when to finish. So you could say if branch len is less than 10, like that 10 pixels is a tiny little branch, then we can finish. Return, else run this. Now we're not quite there yet. We need to figure out when to call it. And we're going to call it for these. So these are the actual individual branches. So we're going to draw a branch of 0.7 times branch length. By the way, REPL probably the best Python browser software ever. But given that it's Australia and 2 p.m. here is the middle of the night in America, most users are in America. When and if they do maintenance, they do it around this time. But we're back. Okay. So we got branch length. We're going to multiply that by 0.7. And the angle is going to stay the same. So I'm just going to put this instead of that. And let's create a branch. Branch 100, 30. Bad input on line 19, 2 brackets. I don't know why. Oh, that works. Speed 100. And there it is, a geometrically perfect tree. Now, with a little bit of randomness, this could get pretty interesting. So let me show you how to create just like a random angle, first of all. Angle is going to not make that much of a difference, but angle equals to rand int. So let's just create a variation here. Maybe we'll go. Now let's just make it 25 to 30, because 25 to 35. So this one isn't going to be perfectly symmetric, but the angle is not going to make that much difference. Oh, 35 to 35. I was looking at that. I'm like, where is the imperfection? Yes, that one. That still looks geometrically the same, to be honest. Maybe that's a fluke. Let's also just change the branch length and we'll see. Let's call that shrink factor. And a random decimal number is created by this thing called uniform. So uniform of, so if we had 0.7, we can go from 0.6 to 0.8. And now we'll multiply by that. Every time you call a branch, the angle randomizes, and that uses the angle. Yeah, that should work. Okay. There you go. That's a little bit randomized. Some branches have only 1 bit. But let's change this considerably. 0.6, 0.9. Yeah. Okay. I think we've overcooked it. But yeah. So every branch is now going to be a little bit different. Some are going to be much shorter than others. Some are going to twist a lot more. And almost makes me wonder if 10 is too short for the final branch length. And there you go. We've got this messy, messy tree. If we went 0.5 to 0.82, shorter branches. Yeah, I like that. Okay. So in terms of making this look a bit more realistic, I'm just going to change, since this is the very last thing I'm doing, I'm going to change this to side by side. And we'll just do a couple more settings to make this interesting. So you can actually set pen size to be branch length over 10. That's way better. When the branch is finished, you can do a stamp, and that's going to be like a leaf. You can make that leaf pen color, make that green. And then when you're done, you can make it the pen color brown. And all of a sudden, you got yourself a tree. I guess we should have probably started with pen color brown here. And yeah, I mean, if we made this a little bit bigger, 0.55, maybe 120 here. Not pen color. I think we should have just made the color. Because now we've got these black filled leaves. Yeah, there it is. A randomized tree generator. Now, it would be possible to actually start drawing these stamps at a much earlier stage, but it's 2:56 and yeah, pretty much running out of time here. Now, there's a couple other things that I just want to share with you. With the email that's coming up, you're going to get links to all of the programs. I think yep. And let me get into my Zoom. New share slideshow. Okay, any questions, you could put them in the chat. For all of the teachers in the audience, what I do is I run small group classes with select students that are hyper enthusiastic about programming, ICT in general. I already do this with about a dozen schools. For students, this is the link to future webinars. I've just I formed a partnership with a company called the Robot that makes microbit parts, and they're going to sponsor 6 free webinars on coding Python together with the BBC microbit. And those are going to be coming on our Eventbrite page as well. I will leave this on the screen for another 2 minutes. Again, if you have any questions, you can just send me a message in the chat. You could even unmute yourself and ask it, or ask me to unmute you. Two minutes again. Oh, so thank you so much for that. I might have some students that would be interested. Okay, thank you, Sylvia. See you later. Okay, Zachi, Anthony, just let me know if you've enjoyed this. I'm going to close this thing in about a minute. The link here, HSA events, has another event coming up, which is going to be a workshop like this on the BBC microbit. Microbit costs about 25 bucks. So if you don't have it, it's probably one of the best programming toys you can buy. So that's everything. Thank you very much. And see you at the next one.